Okay, so I guess final is next Tuesday, right? Next Tuesday. So okay, so again, the final will be released Monday afternoon around 4 or 5 p.m. Right. So the scheduled time for the final, I believe, is 9:30. I forgot exactly what time of the day the final is, but that time will be office hour. You can ask questions. Throughout the day, you can also send emails and ask any question you have. And then we'll be due again on Tuesday midnight. So 11:59 p.m. on Tuesday midnight. The length, the difficulty, the number of questions will be very similar to the midterm. Okay, so we'll pick up from wherever the midterm left off, cover until the end of the class. Okay. All right, so I do encourage people to ask questions because on the midterm, there are some problems that was clear or misunderstanding of the problem, right? Since people just kept going. So again, since it's take home, you have quite a number of time, it doesn't hurt to ask a question, right? If I can't tell you, I'll tell you. That's also I can't tell you, but encourage at least try to ask questions for the final. Okay, and the grading works out this way. So after the final, I'll grade it. Then what I will do on Canvas is I will post the GPA, so out of 4, that I intend to assign for you in this class. So that will be posted probably on Thursday or Friday after the final. Then you can take a look at that GPA and contact me if there's anything about that you want to change. Okay. Then the final grades are due at the registers or in reading week. Once that's submitted, it's very, very hard to change. It takes forever to change once that grade is submitted. So the GPAs will be posted, right? So that's your chance to look at, whether that's a GPA, is it something expected you will get, or if you can compute your homework and the exams. So if you have any question about that GPA, ask them. After the grade has been submitted, it takes months and months to change the GPA. Right? It's a very long administrative process that nobody wants to go through once we get to that point. But I will compute a GPA for each one of you and post on Canvas. Right? So that's sort of the final check you can do. Okay. Any other questions about the final or the grading or fun? Okay. All right, so the grades in this class has historically been pretty high. So I expect the, let's say for undergrad folks, the average grade will be somewhere around 3.6, 3.7. Okay? So that's what the average is. For grad student, you grade from 3.6 above. Nobody ever gets below 3.6 for grad student. So a bit higher for grad student. Right? Yeah. Although if you're a grad student, really nobody ever look at your transcript. So yeah, for undergrad students, think of the average to be 3.65 something. That's historical average for this class. Very, very, very rarely do we have people get below 3.0 GPA in this class. So I don't expect this to happen this year, right, given what I've seen, but that's very rare. We'll see that. Other questions? Okay, so that's a grading and final information. Right? So again, when you study for the final, I encourage you to look back at all the homework you have done after the midterm. Right? Again, they're not hard. There's just a lot of different materials, right, in this class. So you have a wide range of questions spanning the class. Right? So that's, again, you think you have a day or more, a little bit more than a day to do it, but still you have other exams to do. So that will catch up with you. You don't want to leave until the last. Okay? So it won't be a very hard exam, but will still be 7, 8 questions covering a bunch of topics for the final. All right, so that's the for the final and the final grades. So right now, in this class, we'll try to cover markets and then the impact of wind and storage on prices. Okay, we'll cover that. So you won't be able to do the, so at the end, so we'll show some results. We'll show the formulation. It will get a little bit complicated at the end. So that's not something you'll compute by hand. Okay, so we eventually move on to a problem that you won't be solved by hand. You sort of use computer solve, but that's what we'll try to get there. So as a reminder from last time, what we look at is we look at market equilibrium. Okay, so what we said is we have a Q, this is price. Okay, so we don't use P for price. It's because P is often used for power. Okay, so that's why in power systems you see Q being price, right? So we say Q of P is something you will see, a notation you will see. Okay, in most other economic literature, price is P, right? Oh, sorry, yeah, Q is quantity. No, not P. Sorry. So we use pi for price, sorry, Q for quantity. Pi for price, Q for quantity. Again, you want to avoid P for price because that's power. Okay? You want to avoid that power. Okay? So we don't avoid Q. Q is fine. Q is fine. So the reason is we will never price reactive power, or we very rarely price reactive power. So that's why when you talk about money, Q doesn't show up. The variable reactive power Q doesn't show up. So why don't we price reactive power? Right, so once we go into markets, everything is active power. But when you run a system, there are reactive powers. Right? When we talk about type 1 generator, a main drawback is it doesn't generate reactive power. The reactive power is important for the system. But we never talk, reactive power doesn't enter into money consideration, doesn't enter into dollar consideration. Why is that? Okay.
Generators are paid for the amount of active power that they supply, especially if you think of like fuel costs.
Right.
That goes directly into active power.
Right. So for active power, there is a sort of clear cost, right? Fuel cost or the capital cost of building wind and solar, that sort of thing. Reactive power is not that we don't want to price it. Sometimes it would be useful to price it. But once you start doing that, you can sort of make infinite money by putting a capacitor in the graph. Okay, so if you ever price reactive power, the way to make money is just buy a capacitor, put it to ground, and then you're making money once you do that, right? So that's a problem with reactive power. It's very, very hard to price something that can be generated for free. Okay, it's just, you don't need anything to generate reactive power. Okay, so that's why we don't price it for now. So for when we talk about markets, most of the things will be on active power, not reactive power. Okay, and then the market clearing is basically you have a quantity curve, you have a price curve. So your demand curve is the more things you buy, sort of the less you want them, right? So you're willing to pay lower and lower unit cost if you want more of them. Supply, so this is the demand curve. A supply curve is something that goes the other way. It's more and more expensive to produce. Okay. So the general assumption is the demand curve is monotonically decreasing, supply curve is monotonically increasing. Given this assumption, they have to cross, and they'll cross at a unique point. Okay, so these two assumptions suffices to show there is one crossing point. So there's a unique price and quantity equilibrium that comes out of this. They have some Q star, pi star. This is your equilibrium. So for electricity market, what you do is you build up the supply curve. So for power, more specifically for power or electricity. So let's think about how do we build this curve. So where will this curve come from? So how will you build this supply curve in an electricity market? And so let's say you're running some market for, so Pacific Northwest, we don't really have a market, but think of California. So California has a market, right? We want to build up your supply curve. How much money does it cost to generate power? So where does this supply curve come from? Right, the supply curve comes from aggregating all the generators you have, right? So you look at all the generators you have, You ask them how much money does it take for you to generate some power. You put them all together, you got a curve that looks reasonably like this. Okay, you have a supply curve. Go on, yeah. We don't have a market. So we're a central plant system. So there's no bidding, there's no auctioning clearing. BPA tells each generator how much they should generate. So our power system, the generators, are directly governed by DOE. Right? So we have a federal, we're under the federal government. So we don't have a market, as you cannot shop around and build a generator. So you cannot build a generator in Pacific Northwest. Okay? You as an individual investor cannot. The taxpayer through the federal government has to build it. Okay? Now, for example, if you're in New York or California, you could buy a land, build a generator, say I want to be in the market. Okay? That's completely fine. Here we're not allowed. Okay? So it's a federally owned top-down monopoly system. So we are probably one of the last places in the US that runs this way, for historical reasons, mainly because Columbia River. Right. So who runs the Columbia River dam system? Let me know. Right. So the Army Corps of Engineers. Right. So the civilian arm of the Army Corps of Engineers runs Columbia River system. That's 90% of our generation. Okay. So we never had an incentive to become a free market. Doesn't make sense. So you're not going to sell that dam system. You're not going to sell that system to somebody. So there's no reason to become privatized. Okay. Right. So what we're saying is does not apply to us. We don't have this, but most other places in the U.S., Canada, Europe have this kind of market. Okay. Just we are sort of special because of historical reasons. So the supply curve does very much look something like this. Okay. It's because you aggregate a lot of units together. It looks pretty smooth, and then it's harder and harder to generate as you ask for more quantity. So this is pretty close to reality, the supply curve. How will you build a demand curve then, specifically for electricity? It's vertically down. So for electricity, what happens is you're not going to ask everybody how much you will use. Okay, you don't do this kind of poll. For the supply curve, you do go to the generators, ask each of them how much will you produce. Demand, you don't do that. Demand, you basically forecast what people will use, and you have an almost vertical line now for demand, right now for electricity. Okay, so we don't get asked how much we'll use. That's not something the market actually, so the auction of the market is a very one-sided auction. Go ahead. So, right, so yeah, so we'll get to probability a bit later, but suppose you can forecast it, or suppose you know what it is, right? So there's not a range. So basically what this vertical line represents, right, so the right way to think about this vertical line means it's not price sensitive. Okay, so this right line doesn't care what the price is. You just want this much electricity. Right? So this line may move around because of randomness, but still vertical line. So a sloped line means you're actually sensitive to price. Vertical line means I don't care what the price is. I want to be here. Right? So that's the, so for electricity, we have our demand curve is very, very vertical. None of us are very price sensitive. Right? We're not price sensitive at all. So that's the vertical line. Okay, so this is our vertical line going down. And our equilibrium, for example, would be some point here. Right? So that's our equilibrium. Okay, so equilibrium means that, okay, good. So this is our equilibrium. So if you look at all these notations, basically you have a Q star, pi star. So you have the amount, Q, the quantity you want to sell. And then the quantity and then the price you want to sell at. Okay, so now the idea is how much do you get if you get this Q and pi? So now this interesting question, right? So suppose if you look at something like a supply curve, just from the supply side, so think of this is Q, this is pi, this is your supply curve, and you happen to have an equilibrium here. So you have some Q star, pi star. But how much money actually do we give to the suppliers? Right? So I clear the market, but what I get, so remember, this pi has a unit of dollar per megawatt. So this is not dollar, this is dollar per megawatt. Right? So pi. Okay, so let's say we want to figure out is how much money should we actually give to people? How should we pay? How do you convert this dollar per megawatt into something that's just dollars? So we got a clearing price, but it's a price. It's not a amount of money, right? So how much money should this supplier get? I think. Right. So there's two choices to do this. Right? One choice is you simply take this amount multiplied by sort of price. Okay, so that's one choice. One choice is choice number one is sort of payment equals to Q star multiplied by pi star. Right? One has a unit of megawatt, one has a unit of dollar per megawatt. Multiply them together, that's your amount. Okay? So this is something we use in the US, for example. US uses this way. Europe uses a different payment scheme. Can you think of another payment scheme? What this happens? Any ideas on another thing you can do for this? Is there any other way? Right. So this is what we do. In Europe, you don't do it this way. You do some other way. So what is another way to do this? So let's say we do it this way. Okay, let's say we do it this way. As a supplier, do you make money? How much money do you make money? You should make some money at least. Okay, so let's look at this payment and what it says. Okay, so this is interesting economics question to think about. So if you pay this way, right? So what area is Q star times pi star? Well, the area this is basically this rectangle, right? Q star times pi star. Okay, so this rectangle. Okay, so you have this rectangle Q star times pi star. What is the area under the curve? Is there interpretation to the area under the curve? Right, the area under the curve is actually the cost of production. And what is the area above the curve? Profit, right? Okay, so that's the interpretation you have for this kind of payment scheme. You do make some money, right? You do make some money because you have two areas. This is cost. This is production cost. Okay? The amount of cost takes me to produce electricity. The thing above this curve, this is profit. This is profit because this is your cost. You made this entire rectangle of money, so the leftover is profit. Okay. Any questions? Yeah. Sorry? Right. So the difference with the European and US system is the following. In the US, we clear the market, then you get told what this price and quantity is. Okay, so in the US, we do a clear. In Europe, it's a little bit different. In Europe, what you do is you have to tell me your own Q and pi. And if you get used, we don't use a market clearing price, we use the price you have guessed. Okay? So in the US, what your incentive to do is your incentive was to give me the right supply curve, your true cost. The market's job is to figure out this equilibrium and pay you this way. In Europe, you don't provide this. In Europe, what you do is you tell the market, I have some Q and I have some pi. Take it or leave it. And you're saying this is my Q and pi. If you take it, you're not get paid at the market clearing price. You get paid at the price you have guessed. Okay, so let's be sort of be more careful with this. Okay, so let's first look at the US payment system, then we'll look at the European payment system. So in the US payment system, you get paid this way, and you make a profit. This pi star, so if you look at this pi star, this is common to all generators who gets cleared, who gets used. Okay, so if we have many generators, the supply curve is built up of many generators. It doesn't matter. And at the end of the day, you have one price. So this is the common price of electricity we have, and then you got paid this way. Okay, so if you look at something like wind, so what is wind? How does wind sort of go into the system? Wind basically says I have no marginal cost, right? I have zero cost. But what wind how wind contributes to this kind of supply curve is wind will give you a supply curve of the following kind. So the supply curve for wind is basically this. Okay, so zero, I have this quantity at zero price. After some point, I have no more wind. I don't have any more wind. So that's why the curve stops here. Right? So as I integrate more and more wind into this supply curve, what happens to this supply curve? Right? Is this steep more? So what happens here?
The cost will reduce.
Right, but how does the cost reduce? Does the slope change or does it move up and down? Right, so it moves up and down. Right? Because what wind does is you take this whole thing and just shift it. Okay? Right? You take this whole thing and shift it down because you have zero. Right? When you build this, so if you introduce wind into this kind of system, what happens is you basically start to shift this kind of thing down. You have sort of zero cost. Then what wind has, so for wind, right? So why doesn't wind lie about this? Wind has no incentive to lie because it still gets paid the common market clearing price. Okay, so this price does not care what is your particular cost of generating power. It cares what is altogether, what is the equilibrium. Okay, so that's why it gets clear. So that's why wind will just tell the market I have zero cost. Okay? There's no reason for wind not to do this, right? Wind wants always power to be used. And right, so this is the way wind fits into this kind of market. Okay, so it depends how much you generate, then you get paid based on the common price. So now let's look at the European system. So this is EU system, EU market. This is called pay as bid. Okay, what pay as bid means is the following: is each generator submits a pi I hat. Okay, well, each generator was this is my price. It has this price. If pi I hat is less than pi star, less than the total generating cost, if this happens, then generator I gets paid. the amount of power, so QI, the amount of power you produce. Okay. So when you contrast this with the US system, what US system says is, if you get used, you get paid QI times pi star in the US system. Everybody got the same price. In the European system says, no, you get paid by the price you declare. Okay, you can go and declare your price. We are not going, right? So that you don't get paid the market price. So now if you're wind generator, and if you're wind farm and you're in the European system, what happens is you will not just pay zero, okay? Wind does not pay zero. Because the wind says I have zero price, you never make any money. So it's just zero. Okay, for wind it does it, you don't pay zero. So what you should do as wind is you basically have to guess. Okay, so you have to make some sort of guess. You still want to be lower than pi star, you still want to get clear, but you don't want to be too low, right? You lose money now. Okay, you lose money now, right? Okay, any question about the mechanism? So the mechanism is when you bid something in the US, you give your true cost. In this sort of pay as bid system, you just make up a cost, make up a price. Okay, so this is the price I'm willing to pay. Okay. Right. Okay, so these are the two systems we have, mostly for markets, the two kind of markets. Okay. So let's see. So right, so this seems a bit weird, right? Because you're a wind, you're basically guessing what this price is. So what's the advantage of this kind of market? Or say the US market of everybody just gets a common price. Okay. No, because everybody is making up the supply curve. Right? You need to make up, right? So this is a made up number. Okay, this does not need to correspond to any physical thing that has to do with generator. You are asked to just give me this number. Okay. Right, so what this does, one is when you have wind, this actually provides a price floor. Okay, this kind of system, there's no negative pricing. Okay? So most people do not submit a negative number. Because you submit a negative number, what happens? You have to pay people. So this is negative, you have to always pay people. Whereas in the US system, you could get negative numbers. Just because different constraints, right? The constraints work some way. And we have a central clearing price. That price could be negative. If that price is negative, we all, you pay people to take energy. Okay? Whereas this, you do this way, nobody submits a negative number. Because you submit a negative number, you always paying money. So even if the number comes out, right, so you all be always paying. So this is definitely sort of a price floor to people. Well, this has a price floor. So this does not very, very low prices. Okay? Avoid sort of very, very low prices. Because nobody puts bids in extremely low price. You don't pay in zero, you don't pay in negative. And so what this does is sort of actually, in some sense, can encourage wind and solar. Because what happens in the US system is once you have a lot of wind and solar, the whole pi star gets dragged down when you have a lot of wind and solar. So the more renewable you make, so the less you get paid. And then sometimes you break even, there's zero incentive from the market side to build renewable systems. Okay, so that's sort of some of these advantages of this system. The disadvantage is, let's say these are the pluses. Minus, this is not transparent. Sometimes you don't know what's going on. We're all making up prices, right? Who knows what's going on here? And then this sort of has a problem of people trying to guess. pi star, right? What happens is people will just try to guess pi star. You try to sort of hit your price, keep it as close to pi star as possible, right? So you make the most money. You don't want to be more than pi star, but you try to get as close as possible. Once he's doing this kind of guessing, a lot of times this kind of creates very weird prices. There are a lot of spikes and people all try to guess together, right? Because nobody knows anybody's true cost. Okay, so that's two systems. So the benefit, so the US benefits, so you sort of flip this thing around, you got the advantage and disadvantage of the US system. The US system is very transparent. You have true cost, we have true demand, so we clear the market. You know what's going on. Nobody trying to guess this. This is something the system will compute. Nobody needs to guess. Then you can get to negative prices. You can get this sort of weird incentive cycles with renewables. Now, when you get to large enough renewable, you suddenly do not want to build anymore. Right? You don't want to build anymore. And this is a problem for the US system because if you do any kind of computation in the US, you figure out the market probably supports up to 20-25% renewables. Anything more, you're not going to make money of any renewables. Your cost, your capital cost, is more than the money you'll make back by operating the market. Because the more you build, right, your capital cost keeps going up. That sort of is more and more expensive. But then you drag the price down, you actually make for less money. You break even, and the break-even point is not very good. Some sort of 25, 40, 25% renewable level. Okay, so if you follow the California solar debate, it's sort of a very messy policy debate. It's basically that's a problem. There's this misaligned incentives of what to do in the system, right? So you want people to build more, definitely. But then if you build more, you don't make more money, then why would I build more? Like who pays for this concept? Okay, so that's the debate. So there's two systems. Each one has their sort of, this is the US. So each one has their drawbacks. So each one have their sort of good things about them. As renewable gas, higher and higher penetration, what should we do? It's not terribly clear. Where people start to rethink about this kind of markets. Because none of these markets are designed for things that have zero marginal cost. Renewable just because the marginal cost does not reflect the true cost in, right? There's no, so here for renewable, the marginal cost is completely decoupled from the fixed cost. That's the problem people are having with this kind of market. Okay. Any questions? Yeah, go ahead.
Is there an actual value of star, or is that something like if everyone is not saying exactly how much
right.
Does there exist like a value, or is that?
Yeah. No. So there is a value because you stack people's up the quantity and price. You get this staircase function, right? So you go from the cheapest one, you go to the next one. So you get this staircase function. You still have a demand, so you can still put a lot. That give you a 5 star. Okay, good. Yeah. Right. Right, so the problem with this kind of supply curve is once you get to the end of the supply curve, the slope is very large. So if you look at the supply curve, what the true supply curve looks like is the following thing. So so that's a good question. Let's look at sort of the supply curve. A typical supply curve. So this is a US supply curve. I don't know what a European supply curve looks like, but a typical US supply curve looks like something like this. So this is Q, this is pi. Okay, we'll start off as 0. This will start off 0. What this 0 portion does, and this is nuclear, hydro, other renewables, solar and wind, and so on. Okay, so these resources typically bid 0. We're going to market as mass off. Okay, so they go into a 0. They doesn't cost any money. Then this thing will start to ramp to a certain amount. Well, let me draw the slope correct. Yeah. So you think of this thing, being a smooth, this kind of ramp. What is this? What, any guesses? What kind of generation is this? What's the next one after nuclear, hydro, and renewable? So this is nowadays, since we don't have much coal, this is mostly gas. Okay, sorry, this used to be coal, but coal as the US has really become a minor sort of amount of generation. We can think of this as gas plus a little bit of coal. We don't have that much coal anymore, so it's gas and coal. And then what the demand typically comes in somewhere here. Okay, so this is where demand comes in. Sort of you basically the last unit that gets clear some gas unit. Then question is what happens afterwards, right? So you have this curve. This is your gas. What this curve does, it does something like this. What this curve does something like this. So what is these units? What are the things that just go ramp like this? Right, so this is very fast peaking gas or diesel. Okay, things that does not run most of the time, but these are the generator specific designed to pick up this high price. Okay, so that's why when you move demand, sometimes you just hit this thing, and then because the slope is so high, your price starts to drop. Okay, so this is your peak units. This is the peaking. Oops. Draw this again. So this is peaking. Right, so the peaking units. Then really what happens is you have this kind of cap. What happens when eventually you hit this cap? What this is load shedding once you get here. So this means you're going to drop load. And normally we model load with a very, very high price. You want to avoid load shedding as much as you can. But if the load really gets to this point, you just say this we're shedding load at this point. So we're gonna shedding load. So that's so once you hit a cap, so there's normally a cap. Afterwards, you can think of this load shedding. We're not going to serve the load anymore. So for the high price. Yeah. Okay. So this demand sort of moves around in this space, right? So before it used to be this linear region is quite large. Okay, so before a lot of renewables, for example, this linear region is quite large. So your price is sort of smooth in this curve. Now, because you have a lot more renewables, so this is pushing this way. Coal are being displaced. A lot of gas plants are actually peaking plants. So this part is pushing this way. But your smooth part is actually quite small now. So depending on where this demand goes, you can go from 0 to say 500 quite quickly. There's not much range now. Nowadays. Okay. So again, this range was big because coal was dominating. So coal dominates, you have a very slowly ramping in the range. This is how coal works. You replace coal with gas or replace coal with renewables, you squeeze it from both ends, just have a sort of smaller linear region. Right? It's flat on one end, extremely steep on the other end. That's what a typical US supply curve will look like. Right? Yeah, so we don't know. So that's a good question. Right? So in the future is, what if I squeeze out this sort of smooth portion, right? What if all I have is renewables plus nuclear plus hydro and peaking gas? Right? It looks like, we may get there one day. Then what do you do? Right? Does marginal cost even make sense at that point, right? Is your cost just either 0 or 1,000? Like, if you want to operate the system that way? So that's an open question. Right? So that's why this kind of entire theory is, you need to rethink this a little bit. But on the other hand, nowadays, if you work, for example, a trading company, if you go to say the Shaw and you work on their energy trading desk, there's a lot of attention being paid to this market. So what kind of market can make money is a market with this one huge price list. That's where you make money, right? So that's where the supply curve is today. Any other questions? Very interesting times for this kind of energy curve. And that's why, yeah, so energy, you see price, -30 to 200 is not uncommon in one day. Yes, one day. So again, the hope is, right, so the great hope for people is make this thing demand not a vertical line. Right? If this has a slope, you make our life much easier. If demand are responsive, that's again another important part. Can you make demand price responsive? So that's another hope. The last thing this part will cover is bilateral transactions. So bilateral transactions different than the central auction spot market. So this is not a spot market. Okay, so what bilateral transactions do is you can agree with somebody long time, sort of very far ahead of time. So let's say if you build a wind farm and you go to the city of Seattle saying, I'm going to supply you with this much power at this cost. Let's just agree to this and not go through this market auction. Right, so what this does, this reduces uncertainty. So we don't need to depend on the exact realization of demand and all that. Let's just agree, sign a long-term contract ahead of time. Right, if you sign this long-term contract, what is spot market, and then sort of you can take whoever you want to sign this contract. Okay, so this is the way supply and demand can sort of discover each other and work out the contract they want without going to the spot market. So normally this can take up a lot of market share. So in California, for example, I think this is more than 50%. So if you're a nuclear generator, say beside Los Angeles, just go to Los Angeles, say, I'm going to generate use this much power at this rate. So just take it. And that's not to bother with the real-time market anymore. Okay, so that's bilateral trading. And this is again something that happens in the background quite a bit. Okay, so we both shop around, agree on price. So this is another big fraction of how energy gets cleared. Okay, so if you look at in total how energy gets cleared is basically if this is sort of the total demand you have to serve, quite a bit of it is a bilateral trading. And quite a bit of the spot market. So sometimes you lock in your price at bilateral trading, then you go to the spot market here. And the interesting thing is when you do bilateral trading, you don't need to actually own a generator. Right? So this is where speculation comes in. Okay, so if you're doing energy speculation, what you can do is you can go and sign a long-term contract with somebody. And if you're really confident, you can go to the spot market and just buy the energy in real time. Okay, so speculation in the energy market comes between this interface. Okay, you're basically speculating. So you sign, you have a option. You offer people an option, and you can exercise that option based on what happens on the spot market. Okay. The key thing that again that makes energy just so much different than other markets, we don't have storage. Okay, so this is different than other commodity where you can buy it and just put it there. Here, no. Right? So if you're not actually a generator and you sign a bilateral contract, you have to think about what happens if you cannot buy it on the spot market. Okay, so that's why speculation is a bit different in energy compared to other things. Okay. But in general, the market works by just, you have a bilateral transaction. On top of it, you clear the rest based on the spot. Any questions about this? Okay, so let's take a break then to 9:27. Then we'll come back, we'll look at how does wind and storage enter into the picture. Okay, we'll look at some numbers and the impact of, for example, have a storage, how does this market change? Okay, so this is the basic setup, and then come back after 10 minutes, we'll look at the storage. Okay, all right, so we're going to look at storage, right? What kind of impact does storage have in your market? Again, if you own storage, think of how you can make money by owning storage. Right? And the idea is Right? So storage. So what does storage do? Storage moves energy in time. Storage it doesn't have net generation of power. So all it does is it can charge and discharge at different times. Okay, so you have to the thing to remember about storage operation is a net loss of energy. Okay, so a lot of modeling, right, seems to assume storage as you read some of modeling and papers seem to suggest storage can generate power or is not neutral energy. That's not it. All storages lose energy, right? Because second law of thermodynamics. Right? If we all lose energy when it moves around, and you make profit through price differences. Okay, and price difference is really the type of price differences you can exploit to make profit are the ones that's caused by randomness. Okay, but you know there's a price difference and you can use storage. That's sort of arbitrage, right? So that doesn't make sense, right? Otherwise, everybody can make infinite money out of that. So this price difference has to come from this sort of random prices. So that comes from by integrating wind into power. So let's think of how does wind appear into the market. Okay? So let's think of wind. Right? So what wind does, again, we'll take the supply curve to be this kind of some curve with a positive slope. So this is supply. We'll think of the demand curve as a vertical line. Right? We'll think of this demand as vertical line. And we'll think of the impact of wind as coming as a negative demand. Okay, the way we'll think of wind is you have some demand. If you have wind, of course you will use wind to meet the demand first, right? Wind is zero cost. So if you add, whatever the supply curve is, once you have wind or solar or this kind of things, that will be meeting demand. So the impact in this graph is you're shifting demand downwards. Okay, so we're going to think of the supply curve as coming from all conventional generators. Okay, so that does not change when you have wind. Think of the impact on wind as shifting this demand. Okay, so we shift demand when there's wind. Okay, so this is a wind. Okay, so wind is wind just shifts this demand around. Okay, so you can think of this wind as negative demand. Okay. By definition, we're going to think of this as negative demand. Okay, it reduces demand, and then changes the price in this curve. Okay, so if you think about the price, then think of pi as a function of demand. This is pi of d, right? And then what wind does is wind basically gets subtracted off from the demand. So you have x units of wind. Then your price is pi d minus x. So that's the way we're going to think of demand. And then the randomness in price comes from this x is a random variable. So the x is random. So let's assume d is known, pi is some known function, but x is now random to us. So we have some randomness in the price. Okay, so any question about this model? Okay, so this, yeah, go.
I was just wondering, so we don't think of demand as being random, just because we think of it as like, this is just the known value, assuming it's constant?
Right. So okay, that's a good question. So we don't think of demand as a random because we think demand as something very predictable.
Okay.
Right. So yes, that's a good question. So let me be clear about that. Right. So when is random? The demand is not a constant, but predictable. Okay, so we're going to say this definitely not a constant, it's not a fixed number, but we know what it is ahead of time. Okay? The reason again, so of course there's some uncertainty, but the uncertainty in demand is typically much smaller than uncertainty in width. And so the thing to remember, for example, is so let's say for city of Seattle, when we do demand forecasting, a day ahead, we can forecast demand to about 1.5% accuracy, or even 1% accuracy. It's actually one of the first example if you do machine learning energy system is forecasting demand. And any neural network you train will get it to 2% accuracy. Actually, it doesn't take that much. Like you can nowadays you can code it, in an hour, and we'll get you to 2% accuracy. So this is day ahead. For error of let's say 2% or even less than 2%. Okay, so it's very low error. Where you compare to wind, they had error of 25% or even larger. Okay, so this wind is just much harder to forecast than demand. Again, demand, you have many small things adding together. People's lives are governed, pretty closely, follows the hour of the day. Whereas wind, you have to forecast the speed, and then power depends cubically on the speed. So it's very hard to get this small. Okay? That's why we think wind as random, demand as deterministic, but maybe not a constant. Right? Not a constant, but deterministic, no value. Okay, so that's our model. So the randomness comes on the X part, on the wind part. Okay, good. Other questions? Okay, good. So this is our model. So then let's define a function. So we're going to use px here. That's pi d minus x. Right. So this is price as a function of. Right. So this is unit of dollar per megawatt. This is as much, right? So as function of x, the more wind you send into the system, you have a different price. So what this line looks like, is this. Now you have a decreasing P of x. Right? This is decreasing because the more, right? Think of this. The more power, wind power you have into the system, the lower the price is. Right? The lower the price is. Okay. So this is our model of price of wind. And so again, where the randomness comes in as x is random, so where you land on this line is red. Right? That's where randomness comes in. Okay. Let me see. I think my Zoom. Okay, we're back. All right, good. So if you look at this curve, this will immediately sort of points to the fact that integrating more renewables does not mean you make more money. Okay, so that curve points to it. So suppose P of x equal to 1 minus x. Okay, let's just say, that's x as a fraction. So think of 1 as the unit demand you have, x as a fraction of demand you replace by wind. Okay, so let's just see, this, so the price is 1 minus x, something like that, going down. Then let's say, what is the maximum? of wind. That makes sense. Okay, so now you ask, okay, how much wind should I put into the system? Okay, by making sense means if you look at the profit of wind, if you look at profit, this is the amount you generate x times 1 minus x. Okay, this is x times 1 minus x. Okay, so the amount that makes sense, maximum makes sense is you want to maximize this profit. Right? You want to maximize profit. So immediately you can observe that when x is 0, this doesn't make sense, you make 0 profit. When x is 1, this also doesn't make sense. You also make 0 profit. Okay, so there's some intermediate x, right, that will maximize this. So you can solve max x. Right, so this is max squared. So you can take a derivative, you figure out x is 1/2. It turns out that maximizing x is 1/2. So x star is 1/2. Right? So from solving this maximization problem, take derivative, this is 1 minus 2x equal to 0, so x star is 1/2. Okay. So this conclusion is if you are a wind power producer, makes no sense putting more than 50% wind. You start losing money if you start putting more wind. Okay. So this is not a good conclusion, right? If you look at this, you should be worried about this conclusion. Because this tells you somehow this market structure puts a limit on the amount of renewables you can put in the system. Okay, so this is a limit not imposed by technology. This is a limit tip that comes from the market structure itself. You would rather have a market where you say, when I want to maximize the amount of renewables, I should get 100%. So socially, so for societal benefit, you should think that should be the number I get out of it. But the marginal price mechanism, which also seems to make a lot of economic sense, tells you no, there's upper limit. And normally your limit is much lower than this. So this is just, for this example, that's easy to compute, comes out 1/2. Normally you don't even get to 1/2. And normally you're even smaller than 1/2 here. Okay, so that's one challenge we have. So that's something to keep in back of your mind. And for the folks who's going to work in this space, think about different ways to design markets. Is there a market design that tells you the optimal solution is 100%, not say 50% or some other intermediate value? Okay. So things to keep in mind. Again, that's something sort of, Professor Kirschen, for example, works. Gotta think about this every day when he works, right? It's just this market doesn't, for all the economic sense, right? All the mathematical sense it makes, somehow it's misaligned with what society wants, right? What we want to happen, right? So how to line them up is a good question that we have. But the reason sort of people worry about this kind of thing, the reason that California is having a huge fight about solar is precisely because the market, right? This is what the market tells you should happen, is misaligned with the societal goals we have. Right? So that's when you have this sort of big fights. Okay, so something to keep in mind. But this kind of model is a good model to have in mind. Think of, I have some supply curve I have. Then the randomness comes from I'm moving demand along the supply curve. Yeah, I'm just shifting this demand along the curve. Okay. So that's our model of the things we have. Okay. So let's look at what happens when we put a storage here. Okay, so now let's say I have a storage. I have this kind of price uncertainty across multiple time periods. I put a storage there, do I make money? Do I lose money? Does the storage smooth out this kind of uncertainties or not? Okay, so we're going to look at a storage model now. So you won't be expected to solve any of the equations or any of the problem I'm going to write down, but this is just give you a flavor of what the problem looks like. And then if you take sort of other optimization classes, you'll be able to solve this question. Okay? So these are not hard problems, just a little bit out of scope for us. Okay? So this is BESS, this is battery, energy, storage, system. So often you see this as BESS, called a battery energy storage system. So focus on the fact that we have a battery and say not something like pump hydro. It's a battery. So the limits we have here are power, energy limits. We have efficiency limits. Efficiency ratings, right? So with homework, right, you'll see something that's not 100% efficient. Okay, so we have charging and discharging. So this is actually an important thing to keep in mind. Okay, so let's say at time t. So what can we do? We have charging. So the amount that you can charge is lower bounded by 0, upper bound by some maximum value you have. Discharging. D max. Okay. So typically for storage, you need to look at CT and DT separately, not as say CT minus DT. Okay, so typically you need to say whether you're charging or discharging. You can typically we don't talk about the net charge. Okay, so that's in real operations. So why don't we talk about this with net? Why create sort of two positive variables and then say, oh, you're either charging or discharging? Why not just look at, you know, on the net, I'm charging this much or I'm discharging this much. Okay? Right. So the efficiency are quite different for normal batteries. But charging and discharging efficiencies are quite different. And so you normally cannot just talk about as a net, right? So a lot of battery has pretty big efficiency gaps between charging and discharge. Okay, so that's why you need to think about both ways, right? You just really, for actual battery, it's not symmetric operation. For battery, it turns out to be symmetric. Okay, so for this kind of battery, basically you have a round trip efficiency, right? You did some of this calculations in the homework. We ask you to calculate, you know, what is round trip efficiency is. You have a net energy input, you have a net energy output. So you have different efficiency settings for charging and discharging. They don't have to be the same. They don't even have to be close to each other. And one may be 100%, one may be 80%. Okay? So they're not that related to each other, depending on the chemistry of the battery. Okay. So the problem introduces a constraint. What this constraint says is they cannot charge and discharge at the same time. And that's not how storage works. It's either charging or discharging. So it cannot do both at the same time. Okay, so one of them has to be 0. So what this constraint says is one of them needs to be 0. Okay, they cannot be non-zero at the same time. They cannot charge and discharge at the same time. Well, this leads to, so this is a problematic constraint. Okay, so this is a problematic constraint because this is a difficult constraint to deal with. Okay, this is a difficult constraint to deal with because this product. So you have two things that multiplies out to be 0. This is called a binary constraint. This is called an integer or binary constraints. And we don't want to deal with this binary constraint. Okay, so CT times DT 0, this is sort of one of 0. This is a binary constraint. Okay, this is a binary constraint. This is a sort of this is not easy, so it cannot be solved efficiently. Okay, so when you solve problems, you want to avoid this sort of 0, 1 constraints. These are sometimes called integer constraints or binary constraints or the different type of constraints. Your computer do not like this type of constraints. Okay, so for example, you put this into MATLAB, MATLAB will complain and say, I don't know how to solve this problem. I don't know how to solve this sort of binary looking constraints. But the good thing about this is typically you don't even need to enforce this constraint. One of them will automatically come out to be 0. So typically for storage, this doesn't happen. Okay, so the good news, right? Good news. Anyways. Okay, so this actually has some history in the field. So when this was observed, there was a bunch of people working on this problem and trying all kinds of different ways to relax this constraint. They're making it to a linear constraint, they're making a convex constraint, all that. Then people observe that you actually don't need to worry about it most of the time. Okay, so the reason you don't need to worry about it a lot of the time is so just because the economics will work out that they are not one of them wants to be 0. The reason it wants to be 0 is the following. Okay, let's say the price is lambda, right? So this is dollar per megawatt hours, or that's dollar per megawatt. Well, if we put a unit to the time. Okay, so suppose okay, so what if you charge and discharge at the same time? So what if you just have a battery, just sit there and you start cycling? So there's no net output, but you charge and discharge at the same time. What happens? Well, if you look at the cost of this operation, right? This is the money it took you to charge, right? So think of this as the cost to charge. Subtract. This is the money you made from discharging. This is profit. Discharging. Okay, but then if you look at this kind of thing, this is lambda CT1 minus the efficiency. Right? So what you do is, this is the unit you charge, but you have a round trip efficiency of this number, right? This capture efficiency you have in the system. What happens when you have this efficiency is, but this is positive number, right? Your battery is not 100% efficient. Okay? Then this cost is larger than 0. So what this means that even if you don't constrain one of them to be 0, you have a non-zero cost there. So the problem will automatically, the economics forces one of them to be 0. So a mean cost. Will typically be 0. Okay, so that's sort of basically, this is an example of if you make assumption the thing is ideal, you actually run into computational difficulties. If you respect sort of the physical non-idealness of the battery a bit more, actually things are easier. So battery can be a strange space. So often we will work on a problem, so the more ideal the model, the easier the problem is. For batteries, often the more realistic you model it, the easier the problem comes out to be. A lot of difficulty goes away if you actually have sort of better model for battery. So it's a very interesting, at least from a math point of view, very interesting system to think about. Okay, so this typically takes care of the fact. So that's why, because of non-ideal efficiencies, batteries will either try to discharge all of it or charge all of it, right? To not get hit on this sort of round trip efficiency. Okay, so efficiencies are important numbers. And so do not ignore efficiencies when you design a battery. Often those are the things that actually makes the most difference in use. But then once we have efficiency, then we look at charging dynamics. So SOC is something you'll see very commonly when you talk about batteries. So this is the state. of charge. Okay, so SOC just tells you how much stuff, how much energy you have in your battery. Okay? And this couples the operations of battery across time, because SOC at time t is just how much I had at last time. Right, plus how much I put into the battery minus how much I took out of the battery. Okay, so this is our battery model for SOC. Then typically when you work at the battery, you have the following constraint. You have a 0. So of course, the state of charge cannot be a negative number. It's just the amount of energy having a battery. So it's lower bound by 0. But it's also lower bounded by something SOC mean, upper bounded by SOC max, upper bounded by the battery capacity. Okay. Right, so 0 is obvious. This B is obvious. This is how big your battery is. This saying just doesn't make sense for a state of charge to be negative. Where does this sort of number come from? Why do we want to maintain the state of charge between two numbers? That's sort of not the maximum and not the minimum. Okay. Right. So we want to avoid a battery that's very full or very empty, right? Why do we want to do that? Okay. Right. So the degradation becomes very bad. And once you get to here, once you get to here, the reason comes down to the voltage and current are messed up. Right. So if you're very full, right? So you're very empty when you charge, looks like a short. This tries to look like an open when you try to charge. So then that's very bad for the battery. This is here. So these limits the battery degradation. And so normally when you buy a battery, you are so a battery very close to being fully empty or completely full is not very healthy for the battery. Okay, so when you're, for example, you charge your phone, this thing says 100%. You're not charging to the 100% of the physical battery. You're charging to this number. So you can't charge 100% to the battery. Would not like. Okay? So if you buy a battery, let's say this is 100%, how much do you think your battery typically operates? Any ideas of typical numbers for these two? Let's say your phone, or a computer, or an electric vehicle. Right, so this is actually quite tight. Normally you go from 40 to 75. This is a very small range. So when you buy a battery, you don't get to use a lot of it. It's quite empty. So a typical number you can think of is, so this will be large. So typically the most it will let you go down is 20%. The most you can go up to capacity is 80%. This is a very generous range. Okay, your phone is probably not rated this much. Your phone probably has a very much tighter range than this. Your EV will for sure have a tighter range than this. Okay, so when you buy a battery, you get to use about 50% of it, actually, of the physical battery. Okay, again, because pushing it very empty is not good. It really wants to charge once you have very empty. Putting it to be very full is also not. You're putting too much charging into it. Okay, so that's your battery size, right? So typically it's, again, right, so 100% full is not 100% of the battery. There's some range in the battery that's there. Okay, so that's the constraints. Then typically for batteries, you have a no loss or gain constraint. Basically saying after t time steps, your SOC at time 0 when you start it should be equal to SOC at time t, right? So I should have a net constant. My SOC should recover at the end of the day. So you think about you using a, right? So you draw SOC as a function of time. Normally this is 50%. It typically requires to come back to 50% at the end of the day. think of you're driving your electric vehicle, right? You want the same charge every day when you start your vehicle. You're putting this into utility or into a market. You want to start every day the same. Right? So you don't want this. So you want this to be fairly constant by the end of your operation. So that's a constraint we typically have here. Okay. So then I'm going to put things together and look at what happens when you have demand, the battery, and wind. Okay, so we'll look at what happens. We have this kind of system. I'm putting a battery. What happens to the prices? Okay. So here I'm going to write down the results. We won't solve these equations, but the idea is just look at the impact of these two sort of devices in the prices, into the prices. Right. So we want to look at the system price and cost. Right. So we want to look at so this is a traditional generator. Okay, so this is a toy example of a system with generators, batteries, wind, all trying to serve some load altogether. Right, so generators, we take them as something with some cost, or fixed cost. Load, let's say, is given throughout the day. This is something you control. This is random. So that's what we're going to think about this kind of thing. Right? So let's think of this as controllable. This is arbitrary, but no. Okay, so it's not a constant, but we know what it is. This is controllable. This is random. Okay, so different things have different. You should think about them differently in this kind of thing. Okay, so the goal is to control these two, meet this guy, taking this uncertainty into account, and minimize the whole cost. Okay, so that's the goal of the optimization problem. All right, so the formulation is again the mean, the generation cost. Right, so the only thing that has cost is the generators, right? Everything else doesn't have a cost. Subject to load equals to generation plus wind plus battery. And this is across multiple time periods, right? So this is across, we look at solving this problem across multiple periods, right? So battery, this is what couples right? So this is really the thing that brings time together, where all time shows up. Any questions for this? Okay, so let's look at so when you write it out, you have all those kind of equations comes in, sort of upper limit, lower limit, this kind of equality constraint for batteries, all of these. Then we put all those constraints into this optimization problem. Okay, so you have, right, so this is the cost of a generator, battery degradation cost, subject to the load plus generation must be balanced. Subject to have limits on generators. Right? So this together is a sort of huge. You can think of this as optimization problem. This is not a difficult optimization problem, but you won't be asked to solve this, for example, on the final or anything like that. Right? So it's just an example of problem that we can solve. So we have different equality and inequality constraints. And now you're adding some battery into the problem. Okay, then you look at what happens to this. Okay, so if you don't have any constraints, then your cost function looks something like this. And basically what you're doing is once you add a constraint, you want to search over sort of the lowest cost points that satisfy your constraint. Right, so this is unconstrained cost. Then when you put a constraint, you're basically picking some points here that satisfy your constraints. On this. Okay, so what happens when you add wind, right? So when you have, let's say you have two demand and you have some wind. So what this numerical example is trying to capture is when your demand are actually quite consistent with each other, a small change in demand, big change in wind. We're saying the wind is very different in the two time periods. This is typical of what can happen in practice. Hour to hour, demand may not change that much. Wind can definitely change from very high to almost no wind. Okay? So now when you look at net demand, it creates a big difference between the two time periods. Okay? There's now a big difference when you look at the net demand. And then now if you look at so now what happens is if you include a battery, what the battery does is the battery basically moves the demand around. Because what does the battery do? Battery okay, so what the battery does is to saying that once you have load, I'm going to try to make this thing more consistent to each other. Okay, so I have two time periods. Okay, these two are the load without wind. Once wind comes in, one is much smaller than the other. Okay? One is much smaller than the other. To reduce the system cost, what should the battery do? Battery will try to equalize the load somewhat across the two periods. Okay? Battery try to equalize the load across two periods. The reason you want to equalize the load is again the following. So remember, if you look at the supply curve, or the generation curve we have, the power. Okay, this thing. So if you give it a minute to charge. So if you look at these two things, right? So the reason you worry about these two being very different in price and why would this cause a high cost? The reason it causes high cost is the following. Is if you look at the supply curve, so if you look at the supply curve, what happens is when you go higher, your cost doesn't increase linearly. Okay, this shoots up fast. Okay, so you have one small load, one large load, that'll be more expensive than if you average the two loads out. Okay? So this is something called the Essence Inequality. What this says is, if your curve is this sort of convex increasing shape, the thing that minimizes it will be the average. Okay, so you don't want two demands that's very far apart. You want them to be closer in time. So that's where the battery comes in and saves you money. Okay, it's because so if this supply curve was a linear curve, you wouldn't care. It doesn't matter when you serve this. It doesn't matter if you shift it or not. But this is typically supply curve is not a linear curve. So that's why you want to average the demand out. Okay. Any questions for this? Okay, so we're here, we want to average out because the supply curve is not linear. It's increasing. Right? So the slope of the curve is increasing. So that's why we include the battery. Battery basically try to go from this sort of uneven distribution of load, making them more even. Battery will try to average this to load out by moving them across time. They move across time. So basically, you charge here, increase the load. You discharge here, try to reduce the load. Try to reduce the load here. Okay, so that's your battery operation across time. And battery plus wind, again, when you want to have wind, you really want battery because you want things to be more smooth. You want things to be sort of on average and not very far apart from each other. Okay, so this is again, so if you have some net efficiency loss, then typically you cannot make them exactly equal because net efficiency loss. But again, the goal is this will be closer. So your whole goal for a battery is make things sort of constant through time as possible. Okay, to avoid the sort of very high peaks. We avoid sort of the very fast ramping part of the supply curve. Any questions Okay. Yeah, fine. Yeah, this is yeah, this is yeah. So basically, you never charge and discharge at the same time. So you just charge at one period, discharge at another. So this economics makes sense, right? Because this is a lower cost stage, right? When you average them out, it's a lower cost, and you just leave them. Isn't that load here? Yeah, so you really want to average the load out. Like the least cost type of load is a load that never changes. That's the ideal load. That's the easiest thing to plan for. That's the easiest to set your generators for. Right? What wind does is wind sort of disrupts that, right? So wind makes that not possible. So storage trying to recover some of it, make it more even spread throughout time. Okay, and you can look at different costs, right? You can look at different costs. So with different costs, you have system with no wind. So when you look at different costs, you have system with no wind, has a very high cost. System with wind and no batteries, of course, lower cost. Let's be clear, right? So negative wind always lowers the cost. Just with batteries, you can reduce the cost by a little bit. This is actually realistic numbers. The reason we pick these realistic numbers is these are not very far apart. That's the problem with batteries. These typically not, using a battery definitely reduces your cost. Just sometimes you have trouble reducing enough to justify the cost of the battery. For battery, what happens is batteries are still costly. They cost money. So degradation costs money, all this costs money. So you're adding the degradation cost and want to use a battery, there's sort of small differences when you put in a battery. Typically, you don't see very large difference when you have a battery. Right, so that's the challenge with using batteries is that you do want it, right? Often you do want it, but most of the time putting in a battery is not going to make a huge difference in your cost, right? Wind makes a huge difference because wind is generation. Okay, wind will reduce your load. All a battery does is battery just shifts it around, and sometimes shifting it around doesn't make a too big a difference because of the cost of battery. Okay? So the challenge nowadays with battery is one, make a cheaper battery, just make a better battery that's cheaper, more efficient. Second is figure out a way to deal with. There's some way to incentivize battery. Maybe provide more money to a battery. Not just look at the minimum cost, but look at, for example, California, to encourage batteries, putting something called a ramping product. So if you have the capability to ramp very fast, which a battery has, then you get paid some money, whether you get use or not. We're going to pay your money just because you're in the market itself. Right? We're going to create a product for you. PJM took out the product for battery because battery kicked every other generator out of PJM for some market. Battery are the only ones left. And then batteries sometimes just don't feel like doing anything. So that's PJM actually need to create something where traditional generator actually come into the market. Okay, so there's quite a bit of market design questions here. Right, so I guess now is a good time to sort of summarize and conclude the course. Right, so in this class, we look at a bunch of problems going from modeling wind to building turbines, right, to the sort of battery operation and uncertainty. So going forward, again, building turbines is not a huge challenge anymore. We're good at building big turbines. Building batteries, we still have a bit way to go. Like building cheap and large scale and safe batteries, a ways to go. How to handle uncertainty, we have a ways to go. Right? We're not very good at dealing with uncertainties. And then the sort of market restructuring, it seems our market is really not designed with wind and batteries in mind. How to redesign the battery, how to redesign the market is itself an open question. There's a lot of interesting thing going on here. Right? So if you want to look at graduate classes, we cover some of this in more detail in graduate class. We go working in this subspace. you're at a much more interesting time, I'll say, compared to 10 years ago. There's a lot more things you can do. Right, so with that, we'll conclude the class and good luck on the slides. Thanks, guys.